n changes the number of what? Petals. The petals, exactly, right? As n goes up, what happens? Petals. You stop for a second. The number of petals go up, right? Mm-hmm. So if n is 1, how many petals were there? Do you remember? 1. Yeah, and it is 2. There are 2. So there's 1 petal, 2 petals, 3 petals,
so this
4 petals.
Where I was lost.
Yeah?
Because I thought that if you have like an even number inside this sign.
Oh, like how did we create that one with 4? We'd have to go. I need to go back and find that one. I know what you're referring to. Like we had 4 petals before. I think that's because there was something else involved that influenced it, maybe. But in this case, did you get these when you plugged? Did you actually plug them into your calculator?
I did.
Yeah.
So we wouldn't have to know like what that looks like.
Well, it's good if you know what the roses look like. It's really hard for me to come up with a definition of how far you need to know with graphing polars in your head. It's not going to get any more complicated than this. I can tell you that much. I can tell you that much that it won't. Generally speaking, they don't want you to sit there plotting tons of polar points by hand on the AP Calculus test. Like sitting there going like do. It's not a good use of your time. Yeah. But generally speaking, remembering that as n goes up, the number of petals goes up. That's what you need to remember. On the next one, so 15, it says graph this for 0 to 2 pi. There are 2 loops. For each loop, give the restriction. Well, you know which one it is. Which one is it going to look like? It looks like this one, right?
Yeah.
Okay. By the way, I like this pen tip better than mine. I got to switch mine out. Very nice. Okay, so you end up with a graph that looks like you want 1 petal of it, right? There are 2. For each loop, give a restriction theta that shows on theta that shows all of the loop and none of the loops. Oh, sorry. For each loop, give a restriction on theta that shows all of that loop and none of the other loop. So remember what I said? You have what was that integral for finding area? Well, 1/2 integral from alpha to beta, blah blah, f of theta squared d theta. What did I tell you was generally the hardest thing to figure out on there? Generally speaking, the alpha and beta, right? This is exactly what I'm talking about because it's kind of hard to see. Like you have to remember, like what order does it go in? Like where does it start? Where does it end? And I think I already did this one out over here. Let me just see here. Yeah, here it is. So if you do this out, you can start plotting points. Mm-hmm. The key for me is I like to figure out where it starts. Where does it start and what direction it goes in? Where does it start and what direction it goes in? So if you plug in 0 into that, what is sine of 0? It's 0, right? So here's the starting point right there. That's the starting point. And then you plug in, what's the next theta value maybe we want to plug in to sine of 2 theta? Maybe pi over 12. Sure, pi over 12, right? Because pi over 12 turns into pi over 6. And what's sine of pi over 6? A half, right? R is a half, right? So where's that going to? It's going to get closer, right? So you see what it's doing here? It's going to the left like that. Now the real question is after it hits the origin, when is it going to hit the origin? At pi over 4, right?
Oh, yeah.
At pi over 4, you double it, turns to pi over 2, turns into sine of 1. Sine of pi over 2 is 1. 1 minus 1 is 0. So it's at the origin here. The question is after it hits the origin, what is it going to do? Generally speaking, though, polar graphs, they're generally smooth motion. It doesn't jump, right? You don't get those weird like kink discount, like those where the derivative is discontinuous. So plot another point though. Go a little bit further. So go a little bit further than pi over 2. So maybe, so if you plug in pi over 3, right? Double pi over 3, you get 2 pi over 3. 2 pi over 3, what's the sine of 2 pi over 3?
It's
root 3 over 2, right? Root 3 over 2?
Yeah, root 3.
Root 3 over 2. 1 minus root 3 over 2 is negative, right? So where's this going? It's going down next, right? It's going down next.
1 minus root 3 over 2 is...
Yeah, it is. The square root of 3 is great. Oh, no, it's not. I'm sorry. You're absolutely right. I'm so sorry. You're absolutely right. I was thinking in my head the square root of 3 is greater than 2. It's not. Yeah, so what is it actually doing next?
So it's like going...
Look at it. I even labeled it right there.
Yeah,
this is where past self Mr. Seamon is better than current self Mr. Seamon. Every now and then I'm like, huh, good job, Mr. Seamon. Okay, so what is this actually doing? It is actually doing, there's like a little like kink in the graph. So what is it actually doing for a path? It's going like this, right? You see what's going on here? So then what's going to go? It's going to go around like this. So let's talk about the blue petal. Where does the blue petal start? What theta value does the blue petal start at? Pi over what? Pi over 4, right? And then when's it going to get back at what? No. Careful. 3 pi over...
Wait.
3 pi over what? Well, here's the thing. So when you plug in... So what's this... Let's talk about... we wanted to get back to 0, right? So when is sine 1? When is sine 1?
it's...
We want it to be 1 minus what? What is it? 1 minus?
Yeah.
So we need this to be 1, right? When is sine 1? When is sine 1? Pi over 2? When is sine 1? When is sine 1 again?
No.
Just keep all the way back up again.
Yeah, all the way back up again.
5 pi over 2?
5 pi over 2.
Yeah. It's at 2 pi.
5 pi over 2?
So it'd be
Actually,
5 pi over 4.
5 pi over... Wait, hold on. 5 pi over 2. Where's... 5 pi over 2 is all the way around again, right?
It'd be 5 pi over
5 pi over 4 because you're plugging in sine 2 theta. That's what I'm trying to get here. So this point right here, when you're here, right here, like this right here, see that point right there? That's 1. When you plug in pi, into that, you're back at 1. It's 1 away. So that's where. So 5 pi over 4 is going to be when it's back to the origin. So the blue pedal, what's the blue pedal going to be for? The blue pedal is going to be less than or equal to 5 pi over 4 greater than or equal to what? Pi over 4. So you have to be super careful about this.
You get like that whole...
Exactly. So then the rest, if you want to do the rest would be 5 pi over 4. Yeah?
Oh, and you also have to do with the interval.
What? It's the blue one is greater. It's when it's greater than pi over 4 and less than or equal to 5 pi over 4 is the blue one. The blue one. So what about the green one? What would the green one be? Greater than 5 pi over 4 all the way to what? If you only went positive. So the green one, what's the green one going to be? So 5 pi over 4, like this. All the way to what? Hold on, no, but keep going. Remember, you can just keep going.
Oh, that's true.
Keep going. So it's going to be all the way to what? You have to go.
9 pi over 4.
Is it? So you want to go. So you want to get back to. You want to get back to pi over 2, right? So you want to do 2 pi plus pi over 2 all over what? All over 2 because you're doubling it, right? Right, everybody? Everybody with me on this?
Yeah.
So what's that going to be? You have 5 pi over 2 over 2. Wait, did I do that right? No. I'm doing this wrong. It's 2 pi plus pi over 2 like this. So what do you end up with? Wait, I did something wrong here. You want to go all the way around plus pi over 2. All the way around plus pi over 2. Oh, and then add 2 pi again. I'm sorry. Add 2 pi again.
Yeah.
Add 2 pi again. Anyway, do you understand how tricky this can be?
Yeah.
Yeah, it can be tricky. It can be really tricky. We did great. And then look at this one. Oh, we have to break it up into 2.
Yeah.
I'm sorry, you're totally right, Long. That's what you were saying. So where is that blue one? That blue one's from here to here, right?
Yeah, it's from...
I'm sorry, I totally missed it. So it's that one, right? And then, where's the rest? You're absolutely right. Good job, Long. And then this one right here is from here to here. That's the catch. Oh, I see.
Why can't we just keep going from here? Isn't that first section?
So
If you like go past.
So the question is, what's this path? What's the path going to keep looking like? So if we keep on doing this, we started here, right?
Yeah.
We started here, and then what did it do? It bounced all the way around to here, correct?
Mm-hmm.
And then what did it do? It's going to go all the way around to there.
Yeah.
So look, so you could just, so what they did here is we're actually, it's two ways of showing the same thing. It's two ways of showing the same thing.
You could do what you said.
You could do what I said right here, or you could glue together zero. They just basically chopped apart 0 to 2 pi into what covers the two loops. I kind of like mine a little better, where you would go from 5 pi over 4, and then you would add pi over. So it's 5 pi over 4, and you want to go 2 pi more, so you only add pi to that. You only add pi to that. So the actual one, you only add pi to it because you're doubling it. So it would be 5 pi over 4 like this, theta, all the way to 5 pi over 4 plus pi. And I think someone said it, 9 pi over 4. Did someone say it? You said 9 pi over 4. Thank you. Okay, let's look at the last one here. So just to make it clear, the other answer to this one would be, this is the same as 5 pi over 4 all the way to, that was a great catch, 9 pi over 4. Excellent. Okay, so this one right here, it says graph them on the same axis using polar coordinates, find the area or region of shared by both curves, shared by both curves, shared by both curves. Why don't you find the board with somebody else, find the board with somebody else, and try this one. Bring your calculator, you'll need it. Bring your calculator. How'd your picture go? Pretty good? Do you get a picture like this?
Yeah.
Do you see symmetry?
Yeah.
So can you double something instead of doing the whole thing?
Yes.
You can do the whole thing. It doesn't actually change too much, but anytime you can plug in 0, it's kind of nice. So what do you guys integrate from 0 to what? Pi over 4? As opposed to pi over 4 to pi over 2? You can do either one. It's the same half, but when you can use 0, should you? Yeah, generally.
How do you do the whole thing?
Well, you just integrate from 0 all the way to pi over 2, and you don't double it. Oh, excuse me. You would have to use 2 functions. You're right, because it changes. The bounds change. So just do 1. So what did you guys get? You used, let's see, did you get something that looks like this right here? How's this look for you, right? I'm assuming this kind of is what you guys have. I think I saw that in everybody's. 2 sine squared. Okay, so the challenge is you end up with this, right? You end up with that. How many people ended up with that?
We would if
Yeah, 4. You have the 1/2 and then you double it. So it's 1/2 double it, you square it, you pull the 4 out, things cancel, you end up with 4 on the outside. Now, we have done that integration before. Do you remember doing that integration?
Yes.
You have to do it by parts. Is it annoying?
Yes.
Yeah, you don't really have to do that by hand anymore. So it's fun. They say use the formulas, which is just the table of values. You could use your calculator. Do that right now. Use your calculator right now and do that integral right now, just so you know you can do that on your calculator. So demanding. Oh my God. Okay. So you have, this is the shape you're dealing with, right? You're dealing with something like this. That's what you're talking about. So what you have to realize is when you integrate, what are you adding together? An infinite number of what? Sectors, right? Each sector goes from the origin to, you're sweeping out these sectors, right? You're sweeping out the sectors. So there's a sector here, there's a sector there, there's another sector right here. So it doesn't include anything over here because the sector is glued to the origin. It's glued to the origin. Imagine you have a piece of string tacked to the origin, and it's a stretchy piece of string, and all you're doing is you're sweeping out the area by having you're stuck on one end, and what are you doing? You're going out a little bit and sweeping it up this. So what are you only sweeping out? You're only sweeping out the area you want. You don't touch anything outside of that area because can you always connect? Look over here. So if you have this curve right here, if you're at the origin and you're anywhere here, what are you always going to get? You're always going to just go through the area you want. Now, remember when we had Cartesian coordinates, if there was a function and then there was another function underneath it and we wanted the area in between, what did you have to do? You had to subtract the function underneath, right? So up and down was defined by the y-axis, right? Our y-axis is now whatever direction is towards the origin. Anybody read it? It's the enemy's gate is down. The enemy's gate is down. What is that from? Anybody know? I'll give you $10 right now if you can tell me where that's from. Literally, I will hand you $10 right now if you can tell me where the enemy's gate is down. Oh, no, really? No one knows the phrase "the enemy's gate is down"?
Can we get a hint?
Okay, I'll give you a gold star if you can get it in 10 seconds. 10, 9, 8. Improper integral y.
Because
What?
the bound is infinite.
Because the bound is infinite. The bound is infinite. So on this one, we talked about this before. Do you remember, does this converge or diverge? Do you remember? It converges, right? And do you remember how to do this limit? What do you have to translate it into?
So you have to change the infinity to what?
Yeah, and then you do what in
And
front?
limit
Limit as b goes to infinity. Yep. 1 to b of 1 over x squared dx. So you do the integral of that, and what do you end up with? The limit as b goes to infinity. What's the integral?
-1 over x.
So negative x to the
-1.
-1, and you're going from 1 to b, like that,
Yeah.
right? So when you plug these in, so you get the limit as b goes to infinity, and then honestly for me, what do you think I consider to be the hardest aspect of this problem? What do you think?
The algebra.
The algebra. What specific part of the algebra?
Just like all the negative signs.
Yeah, so you have this, right?
Oh, and then you have to add.
Minus -1 over, right? You see what I'm saying? See what's going on here? Did I write that correctly? I think I did.
Yeah.
So you have to like the minus the stuff. So then what happens to this? You end up with this goes to 0, and you end up with what? 1, right. So if you, for me, it's the negative signs. Yes.
So, why? I mean, like, of course, there's a reason why we do.
Of indefinite integral that's not always obvious. Why is this one an indefinite integral?
If you plug in two.
It's an asymptote. You can't plug in 2. 2 isn't in the domain. So if you try to integrate across a discontinuity, what happens? Weird stuff. I threw one of those at you on the last test to see if you could notice it, and many of you did not. If you try to integrate across a discontinuity like a vertical asymptote, sometimes you'll get a number like 7, right? And you're like, That's clearly the answer. And there's no like red flag that it isn't, because a red flag is like negative a trillion or something that really doesn't make sense. But it's not always going to be obvious. You always need to check for discontinuities. So in this case, what do you change the limit to? So it's going to be, you're integrating what though? You're not going to integrate to 2. You're going to integrate the limit as b approaches 2 from the left. 2 from the left, right? Because you're going from 0 to 2 of b like this. Like, does everybody see this right here? Is everybody good with that? Can you integrate that for me? Can you integrate that for me? Oh, come on, you can integrate that. Really? What is it? What do you have to use?
No, I don't think you need W sub.
You don't need, yeah, so careful with that statement, because sometimes W substitution is very helpful even when you do, quote, need it. Like, needing W substitution isn't always obvious. You know what I mean? Like, sometimes people can integrate things in their head that other people can't. So what do you think the integral of that's going to be?
So would it be like a negative x minus 2 to the negative 1?
So what happens if we said negative x minus 2 to the negative 1? Does that work? Drop the negative 1 to the front, it makes it positive, and it becomes negative 2. And the chain, what does the chain rule kick out of the x minus 2? Just a 1. So is it okay? So again, it's the limit as b goes to 2 from the left of this, from 0 to what? 0 to b. Now, this is a, where could I put that negative sign just to make my life easier?
Just
Kick it out to the front. I'm going to do that. So it's the negative b, 2 to the left, of x minus 2 from 0 to b. So what's that going to be? Negative.
You forgot the negative 1.
Negative 1. Thank you. That's important. B to 2 minus. So what do we have here? 1 over b minus 2, right? Minus 1 over 0 minus 2. Is that correct? So if we approach b from the left, that means smaller than b, smaller than 2. Sorry, smaller than 2. Minus 2 is going to be a really, really small, what type of number? Negative number. So 1 over a really small negative number, what does this go to? Negative infinity. Careful, so it's going to be negative infinity minus what? Or plus what? 1/2. So what's this going to do? Diverge. Diverge. You like my boom? I like it. Continuity, what about in this case? This is the one I hit you with, and you guys just ran over it. You're like, didn't even notice the speed bump. You're like, my car no longer has wheels, but I am still in my car. You know, like, you're not going anywhere.
0.
The 0. You can't plug in 0. So what do you have to do to this? If you take away a finite number of x values from an integral in 2 dimensions, it does not change the overall value of the integral. A finite number of points does not change the overall value of the integral.
It changes where it diverges or converges.
Well, it makes it so you can evaluate it, but the point is it doesn't change the overall. It doesn't change the overall value of it. It's kind of cool. I know. Boom. Kind of cool, huh? Because there's no width. That's why. One number has no width. That's the best I can do. Okay. So what? So we change this into what? The integral from -1 to what? We can say 2, 0. We could say 2, 0 right now, just for x to the 4th dx plus what? Integral from 0 to 2 of 1 over x to the 4th dx. But can we plug in 0 into either one of those? No, we can't. But we break it apart because you need to choose the same value at the beginning. So what do we have here? The limit as, let's say, b goes to 0 from the left of, not 0, -1 to b of x to the -4th dx, plus the limit as, let's say, c goes to what? Z goes to 0 from the right of the integral of c to 2 of x to the -4th dx. And then you'd have to do both of these. I'm not going to finish this, but do you understand the setup? The key realization is, can you integrate across 0 on this thing? No, you've got a vertical asymptote. You need to do it separately. Don't try to cross it. Bad things happen. Okay. How you feeling about these? Just a good refresher here. Remember the discontinuities? Remember the discontinuities? Now, I don't think what's